inviting me. It's too bad I can't be there in person, but hopefully next time. So I'll tell you about this recent paper that I wrote called Axions, Higher Groups, and Emergent Symmetry. It's a paper that I did in collaboration with Daniel Brennan, who's a postdoc here. And there's also two principal earlier works that I've referenced up there. Okay, so this talk is kind of about an elementary thing. So we're going to get axions. By that I mean a periodic scalar. A, and we'll call the periodicity 2 pi f, which is the decay constant. And this talk will happen exclusively in 4 space-time dimensions. And basically, for most of the talk, we'll just be concerned with the question, what is the global symmetry? So we'll have some model of axions, and we'll ask, what is the global symmetry of a theory of axions, and what can we do with it? And this question, while it's seemingly very basic, has a kind of cute answer. Okay, so let's start with just a free theory of axions. So we won't couple the axion to a gauge field yet. So there are 2 symmetries to discuss. Okay, so the first I'll call 1 super 0. And here I'm introducing a notation that will be common throughout. This superscript 0, this means the form degree. So in this case, I'm talking about a 0 form symmetry, which means an ordinary symmetry. And just to remind you, a p form symmetry is something that acts on operators of dimension p. So a 0 form symmetry acts on point-like local operators. Higher form symmetries, which we'll encounter shortly, act on extended operators. Okay, so this is a 0 form symmetry. And what's the current? So there's an ordinary current with 1 index. I'll write its Hodge dual star J1. And this is just F star dA. Of course, this is closed by the equation of motion. And this is a very familiar, this is the axion shift symmetry. So you can take the axion A and you can shift it by a little amount epsilon. And this symmetry is spontaneous. And the axion is the associated Goldstone boson. Okay. Now, if you're just talking about a free theory of axions, there's one other symmetry that you should know about, which is a 2 form symmetry, U1 super 2. What can we say about this? Let's write its current. So this a 2 form symmetry, continuous 2 form symmetry should be associated to a current with 3 indices. So I'll write the Hodge dual of it. It's easier, which is just dA. And if we want to be conventional and get integer charges, we'll 1 over 2 pi f. Of course, this is tautologically closed. So that current is conserved. Now, a 2 form symmetry, as I've indicated, should act on objects of dimension 2. What are they? So we can make a string as follows. So here we're going to put some extended operator. This is a transverse space. So this will be, this is the transverse space. And surrounding this string is a little cycle, 1 cycle. And the statement that the strings are charged under this 2 form symmetry is the statement that the axion winds around. So here we get an equation like this, where n is the string charge. Okay, so we have this two-form symmetry where the axion winds, leading to these strings. And one thing maybe to comment on is that the analog of the Coleman-Merman theorem implies this symmetry is never broken. Okay, so we have the zero-form symmetry, which is the axion shift symmetry, and we have the two-form symmetry, which measures the charge of strings. And the strings are allowed precisely because the axion is periodic and can wind. Now, it's useful to describe the symmetry also by coupling to background fields. So how would we couple to background fields? Well, we know what we're doing usually with an ordinary symmetry. So for an ordinary symmetry, we'll couple the current to a background ordinary gauge field. Oops, I should get my notation straight. So we'll have A with one index. And for the two-form symmetry, we should couple to a gauge field with 3 indices.
Sorry, Clay,
fields.
Sorry.
Yes.
Of the two symmetries you talked about so far, the two currents, was the first one conserved because of equations of motion, and the second one is a sort of
yes. So the first one is present because right now I'm just discussing a free periodic scalar, and then I'll subsequently add interactions.
That's what I was going to ask you, because it sounded like if the statement del square A is equal to 0, the current conservation, right?
Yes, exactly. So the shift, the axion having the exact shift symmetry is a statement that the theory is free. So soon we'll discuss something more interesting where an axion couples to a gauge field, and then we'll see what becomes of these symmetries.
Sorry, and just to make sure I understand that, suppose I had theories with only derivative interactions. Wouldn't the theory always have an exact shift symmetry, even though the theory was not free?
Yeah, yes, that's true. But then the current will get modified. What will happen is that those derivative interactions will modify the expression for J1. So the equation of motion won't be that d squared A is 0. Right,
but you'd always be able to find the current because it's just the canonical momentum that gets modified in terms of derivatives.
Yeah. Okay. Absolutely.
Thank you.
Right. Yeah. So, but just to clarify my previous comment, the interactions that I'll consider soon involve A explicitly, not just its derivative, and so then this shift symmetry we'll have to reinvestigate.
Thank you.
Okay. So so we're going to have 2 background fields, and it's easy enough to write down the action should be coupled to background field. Of course, I didn't write the action without background fields, but this will serve as a definition for us. So, okay, coupling to the background field for the shift symmetry is easy. Since A is a Goldstone boson, we just kind of Stuckelberg it here. And then the other one has a kind of mech type coupling where we write A3 dA. So this is the action coupled to background fields for these 2 global symmetries that are manifest in a free theory of a periodic scalar. Okay, are there questions about this? Okay, very good. So, of course, we're mostly not interested in free theories of periodic scalars, but we'd like to discuss axions coupled to gauge fields. So let's do that. So in this talk, for simplicity, I'll consider U1 gauge fields or SUN, but everything I say could be generalized to other gauge groups. The details are slightly different. So let's first look at the symmetries briefly of the gauge field sector. I won't go through them in detail. So before coupling the gauge fields to the axion, what would we have? So if we had a U1 gauge group, well, then there are two interesting symmetries. So there's what I would call U1 electric and U1 magnetic. That's what the E and M subscripts are for. They're both one-form symmetry. So electric, magnetic. And they act on lines. So either Wilson lines or 't Hooft lines. For SUN, something a little similar. We can have ZN1, one-form symmetry. You could think of this as just a discrete analog of the electric thing that exists in the abelian gauge theory case. And this again acts on Wilson lines. Okay, so this is supposed to be a lightning reminder for you of what the symmetries of these gauge theories are. Here, I should comment that I'm discussing the situation without matter. Matter modifies the situation a little bit, and will be discussed in a little while. Okay, so any questions? I didn't explain it, but I just stated it, but feel free to ask questions.
If you put appropriate matter, it breaks the electric symmetry while retaining the magnetic one for the U1 side?
That's right. More generally, if you have matter of, say, charge Q, you would break U1, 1 to ZQ, 1. So if Q is 1, you break it all the way. And this is a statement really about screening. So when I say that there's an electric one-form symmetry that acts on Wilson lines, what I mean is that you can measure the charge of a Wilson line, and the fact that it's a symmetry means that it doesn't matter what distance you pick to try and away from the line to try and measure the charge. Whereas if you have dynamical charge matter, then they can screen the line, and then it would depend on distance, so it's not a symmetry anymore. But if you only have matter of charge Q, you would still have the charge mod Q could not be screened. Make sense?
Yeah, perfect. And in the case of the axion, exponential of the axions would be charged operators, right? So it would start.
That's right, for the shift symmetry. Yeah. Yeah.
Thank you.
Okay, good. So just as before, let's also, so this was a little aside, we can also couple to background fields. So let's do for the U1 case. So e.g. for U1 gauge theory, we would have a background field B2E, which is associated to this U1, 1E. And we would have a two-form background field B2M, which is associated to the magnetic one-form symmetry. And the action is quite easy to write down. It would just be 1 over 2g squared F minus BE squared plus, and then a kind of magnetic coupling So that's the action for U1 gauge theory in the presence of background gauge fields for both the electric and the magnetic one-form global symmetries. There's something similar you can do for Zn one-form symmetry of SUN. It's a little more technical, so I won't do it right now. Okay. Any questions about this? Okay, so we saw the symmetries of the axion theory. We saw the symmetries of Maxwell theory or of SUN-Yang-Mills. Now, of course, we like to couple them. So let's discuss axion-Maxwell theory. Or Yang-Mills. And then, of course, the key thing is that we're going to include in the action, in addition to the terms defining those theories individually, a new coupling, which looks like the following. So here K, so this is a normalization constant. This K is kind of important. K is an integer. So there's an integral coupling constant. And here I've written trace F wedge F. So that's the notation as if I was doing Yang-Mills theory. If I were doing Maxwell theory, then I just omit the trace. Okay, so so this is, of course, the interesting coupling between a periodic scalar and an axion and gauge fields. And we like to investigate what it does to all these symmetries and then make some comments about that. Okay, so let's just go through them. So what happens to the shift symmetry? Well, this is broken. As I previously commented to Shiraz, here we have an interaction that includes A explicitly. So that can generate some kind of potential effectively that that breaks the shift symmetry. And in this case, what it breaks it to is ZK0. So A can shift by k 1/kth of its periodicity, where k is that coupling constant. So in the minimal case, when k is 1, you break the shift symmetry completely. Okay. Now, interestingly, a similar thing. So here, let me below here, let me just discuss axion-Maxwell explicitly. By that, I mean that I'm going to discuss in detail the case of gauge group U1, and then I'll make, it'll be easy to generalize from that to the non-abelian case very quickly. So, okay, so then we have a U1 electric. And this is also broken. This is again broken to ZK, one form symmetry. This is much less obvious that, that the electric symmetry is broken. And to do that, we're going to use the equations of motion to see that. So what is the equation of motion? The equation of motion says that D star F equals, let's get the factors right. And so it says this, and I remind you that star F, that this is basically star of the two-form electric current. So this is the thing that was previously closed by the Maxwell equation of motion that was telling us that we had a one-form U1 electric symmetry. Now we find that this current is not conserved anymore. Instead, there's effectively some kind of electric current on the right hand coming from this term. So you can use this to make a conserved now. So you might look at this and say, well, it looks like the current is just no longer conserved, so maybe there's no electric symmetry at all anymore, no one-form symmetry at all. Actually, there is a ZK. Well, if people are interested, I guess I can write. Let's see. Let's write the one way to convince oneself. Is that we can write the gauge invariant charge operator. So we could try to make a one-form charge. Which we would write like this. So this is an integral over a surface, an arbitrary surface. And so you should first close your eyes and delete this this A term. That would have been, then this would have been the integral that measures the electric charge of a line, or the electric charge on some surface sigma. And that would have been the natural charge that we would have associated to this U1 one-form electric symmetry. Now we no longer can integrate just star f. We have to shift it by this axion coupling term A wedge f. And then when we do that, to make it well defined, this L has to be an integer. And so we can only do it for some kind of discrete multiples. So that's why we end up with this ZK one-form symmetry.
So is this equivalent to saying that on the right-hand side of your d star f equation, if you integrate the right-hand side over a 3 torus, it's always quantized in integers modulo k?
Yes, because I have a k there.
Yes.
Yeah, exactly. Yeah. Right. So you know, when you see an equation like this, you're sort of tempted to move the A wedge F term to the left-hand side and redefine the current. That's essentially what I'm doing. But then I pay a price, which is that the axion is not quite well defined. It can shift around some cycle. So that means that the current that I get by doing that is not quite a well-defined operator, but certain exponentials of it are well-defined operators. That's what I've written here. More questions? Okay, so so we've looked at the shift symmetry and the electric symmetry, and we saw that they were broken to ZKs, but the other symmetries survive. So meanwhile, this two-form string symmetry is preserved. Why? Well, dA is still closed. No amount of fiddling with adding interactions involving an axion is going to change the fact that D of A is closed. A similar kind of applies to this magnetic symmetry. This is also preserved. And that's just because, well, D of F is 0. And again, no kind of fiddling with interactions is going to change that. We have to do something more drastic to violate the magnetic symmetry or the string symmetry. Okay, so we've learned that this axion Maxwell theory seems to have symmetry seems to have the following symmetry. It seems to have this U1, 1 magnetic, ZK, 1 electric, ZK, 0 shift symmetry, and U1, 2 string symmetry. So it seems to have all these different pieces. And in fact, if that were all there was to it, I probably wouldn't be giving you a talk. But instead, there's actually a kind of novel feature here, which is that these are combined into what's called a higher group. So if you've never seen this term higher group before, don't be alarmed. I'll try to explain it. But essentially, in words, to say what it is, it's a kind of non-abelian generalization. It's a kind of non-abelian group that is possible when you have form symmetries of different degrees. So in a sense, saying that the symmetry is a product of these different factors is kind of wrong. And we'll try to quantify how it's wrong. Okay, so we'll do it in a couple different ways. So let me explain by coupling to background fields first. This is kind of the slickest and most technical way to do it, but we'll get to the answer fast. Okay, so let's remind ourselves what the notation was for the background fields. The friend of this U1 magnetic symmetry was called B2M. This one was called B2E. This one was called A1. And this one was A3. So I said these were gauge fields, but I didn't really clarify what it means for them to be gauge fields. Well, gauge fields means that there are linear gauge transformations. Everything looks abelian here, so the gauge transformation should at least naively be abelian. So, for instance, we could shift 2. Could add D of some local 1 form. Same for, say, A3. D of some local 2 form. But what we'll find is that although these are the right sort of linear terms in the gauge transformations, there are we require to make the symmetries really work some interesting nonlinear terms. So these are going to be some nonlinear terms. That depend on other backgrounds. So this is, if you think just kind of conceptually, this is like saying that the gauge transformation rule is more similar to what it is for SU2 than it is for U1 cubed. Right? The difference between saying you have U1 cubed or SU2 symmetry is in the nonlinear terms in the gauge transformations for the background fields. And something similar is going to happen here. And another analogy that maybe I'll say before writing the explicit formulas is that this is essentially a Green-Schwarz mechanism for global symmetry. So usually when one discusses the Green-Schwarz mechanism, you have some form field, usually a 2-form field, but sometimes a higher form field if you're in even higher dimensions. And you find that under some gauge transformations for ordinary gauge symmetries, the 2-form field must, or higher form field must transform. Usually in that context, the higher form field is a dynamical field that's summed over in the path integral. Here we have something a little bit logically prior, which is that it's a global symmetry. This is a background gauge field. Okay, so without further ado, let's try and fill in the blanks. And the way to do it is, again, to try and write the action coupled to background fields. What's S? So some pieces of it are easy.
Sorry, Clay, just to understand, you're saying that if you took the naive transformation laws, you would find that the theory was anomalous. Is this right? And then you have to fix it up by...
It's even worse than being anomalous. It's worse than being anomalous. So anomaly, in the usual terminology that, well, it depends exactly on what you mean by the word anomalous. So that word is pretty overloaded in physics. So let's distinguish some possible behaviors that we could find. So if we just use the naive gauge transformation laws, one thing that we could find is that the action shifts by a C number. That's one thing we could find. And that we don't mind. That's what's called an 't Hooft anomaly. That's an allowed behavior. But a worse thing that we could find is that we could find that the action shifts by an operator. Right? A non-trivial operator, not a multiple of the identity, and a multiple of a non-trivial operator.
Right.
That's actually what the difference is between, say, U1 cubed and SU2 global symmetry. Right? If you say, suppose I'm in a theory where I have 3 currents and I'm unsure whether the symmetry is SU2 or U1 cubed, and I just say, well, I'll do it's really SU2, but I'll do the correct linear transformations and I'll leave off the nonlinear terms. The action will shift by an operator, not a non-trivial operator, not by a multiple of the identity. And so that's what we would find in this situation as well.
Wonderful. And
so
if you did a naive classical analysis, you wouldn't see this. It would look like the naive shift would be a good symmetry of the theory. Some quantum effects that make this happen. Is this right?
Well, it's sort of, I mean, I think it's classical at the level of the A wedge F term, basically.
Oh,
it's very easy from the A wedge. Yeah.
Okay.
So once you have that term itself often arises from one loop effects. But once you have that term explicitly, it's a classical analysis of that term.
I see. What's confusing me is that the analysis you've done so far seem to indicate that it was a symmetry. But you'll show us why. Just the knife thing was a symmetry. I'll just wait.
No, so the thing is that they will look like sort of symmetries on their own. So like if you take one into account without the other, it will look like they all work. But so the nonlinear terms that I didn't write for, say, B2M will not involve B2M. They'll involve the other fields.
Okay, I understand. Thank you.
And that way it will evade your objection. But actually, your comment is anticipating sort of how you can use these funny features to do some physics, which is what we'll do at the end. Okay, so let's try and write the action coupled to background field. So some part easy. So okay, so those parts are easy. Now what will we do for the kind of magnetic parts? Well, let me write them like this. So here I'm going to introduce G4, which is dA3. And we'll see that there's other terms there. Well, we'll write them presently. And similarly, I will also write the magnetic term as C wedge H3. So here F is DC. So C is the U1 dynamical gauge field. And H3 is something like the field strength of the two-form magnetic field. So far we've written only we've tried to write only the terms that we had for the theory separately, but not the interaction term. And of course, the interaction term is where things are going to get tricky. So, okay, what do we do? So we have what am I do here? So I'm going to introduce X. So X will be a 5 manifold. And the boundary of X is the physical spacetime. There's a trick for writing the kind of problematic term that we have to deal with. And the point is that once I get to do that, then I don't have to deal with the F, that A is periodic, because I can just write dA. So I can try to write something like this. Okay, so this formally looks like the right, like the right kind of Lagrangian. In particular, all the currents couple linearly correctly to the correct background gauge fields. I've ensured that. But I have a problem. So first of all, before going on, is it clear what I did? Is it clear how I cooked up this action? Right. I mean, all I'm really saying is that A is the Goldstone boson for the A1 shift symmetry. So I have this dA minus FA1. The photon is the Goldstone boson for the electric symmetry. So I have this F minus BE2, and wherever I see F, I replace it that way. And then I just had the standard magnetic couplings to the two form and magnetic backgrounds. And then for this axion term, I tried to write it in one higher dimension so that I basically always have to deal just with field strengths, so that I don't have to deal with naked gauge
sorry,
fields.
and where did the G wedge H3 come from?
That's C. Excuse me. This is C.
No, I am.
Here you mean? Sorry, that's a bad note. That's a badly written C. So C is the U1 gauge field.
Okay, thank you.
So previously I had F wedge B, and I'm writing it in terms of the field strength H, so that everything will become clear in a moment. Okay, so so I have this looks good, but I have a problem here, which is that I'm trying to do 4-dimensional physics. And if you're trying to do 4-dimensional physics, it's not very good if you have some 5-manifold line. So check. We need to check that choice of X drops out. This means that the dynamics is really 4-dimensional, even though I wrote explicitly a 5-manifold X there. And if you try to check that, you will find that you will need some nonlinear terms in these field strengths G4 and H3. So what will you find? You will find that you need the following term here. BE wedge BE with some coefficient. And over here, you will need a similar kind of term with different backgrounds.
Sorry, Clay, just to understand.
Yes.
You had to make this thing 5-dimensional because you wanted it in terms of DAs so that you could introduce this A1. I mean, you didn't know how to gauge if it was in terms of A.
Yes, that's right. Yeah, I know that exactly. Yeah. Yeah. That's exactly right. So because A is like a gauge field because it has this shift, it's easier to couple to its field strength. So this is just a technical trick for trying to write the action. But then what you see is that you need these additional nonlinear pieces in the field strength. Notice the resemblance to the Green-Schwarz term. Green-Schwarz kind of, yes.
Sorry, one question. So
yeah.
These electric symmetries were broken to discrete symmetries, right? So the zero form and the one form electric.
I've glossed over a couple little things there, but that means that A1 and BE2 are discrete gauge fields.
Okay. Okay.
But it only, practically speaking, all that means is that they themselves are flat. So there's a field strength for H3 for the magnetic one, but not for the electric one.
I see. Okay. Thank you.
Right. So notice the simultaneous conceptual similarity here to both a non-abelian ordinary symmetry, where the field strength, of course, has the nonlinear term in the gauge fields, and also the Green-Schwarz mechanism, where the higher form field gets its gauge invariant field strength involves kind of a Chern-Simons-like coupling on the form fields of lower degree. Here we have something similar, both happening at the same time. Okay, so this is how to see this and it should be clear that we have these additional field field strength terms here. Of course, you can go back and fill in that there were some interesting ... dots in the gauge transformations, because what we're learning is that the H3 and the G are their gauge invariant only when in this combination. And so that adds some interesting ... dots up here. Okay, so this was a way of thinking about higher group symmetry, that kind of explicitly in terms of the background fields. What does it mean in terms of how you source currents at the nonlinear level? And there's another conceptual way that I will briefly mention, which is that you can also view this in terms of the charge operators. So, if you have a
question. So this phi manifold integration, instead of that, if I just were to do to write the previous term, which is A with A wedge F, then as you say, I don't quite know how to introduce this capital A1 in that term. But if I ignore this symmetry, it seems that the structure would persist, right? Because your G4 has a correction in terms of only BE2 and does not involve A1. So you should be able to explain this correction even without going to this idea of phi manifold.
Yes. In fact, you can. You can do it directly in 4 dimensions. You'll just end up coupling like A1 to the Chern's term for the U1 gauge field. You can see it by just taking this term that I wrote as an integral over X and just trying to brute force integrate it by parts and see what all the terms that you generate are.
Okay.
So you can do that. That's a way to proceed as well. I just find this a little more transparent. Okay. When you do it that way, you'll end up with a bunch of couplings that don't look quite like they're all manifestly okay. And then they'll kind of conspire together.
I see.
Okay, so let's also try to view this, at least conceptually, in terms of charge operators without presenting the details. So we wrote charge operators for one-form symmetries above. That means you could integrate over some surface and measure the charge. So, for instance, the ZK one-form symmetry tells us there's some kind of surface operator. This is the charge. I wrote it above. And the ZK0 is some kind of domain wall. It's a kind of axion domain wall where the axion shifts by 1/kth of its periodicity. Now, what does this kind of funny higher group global symmetry that we're deriving here, what does it mean in terms of these charges? Well, it means a kind of interesting fusion law. So if you take a surface and you intersect it with another surface, here I'm talking about these ZK1 one-form surfaces, what you'll find, according to the formula, is that at the intersection points, there will be G4 flux. So that's a kind of operator product expansion rule. So you have these two surfaces, these two electric one-form symmetry surfaces, you intersect them, and at their intersection points is some gauge invariant flux. There's, of course, a similar thing interpreted with the other formula. So if I take a surface and I intersect it with a domain wall, then I find H3 flux. So that's a way of interpreting this higher group symmetry, perhaps more physically, as a kind of operator product expansion rule for the symmetry defects themselves. Okay, so we can also analyze this So that was all I wanted to say for right now for axion Maxwell theory. Let me say that you can also, we can also do non-abelian Yang-Mills. So then we have ZK zero form symmetry. We have the ZN one form symmetry of SUN. We have the two form symmetry of the string. And this again becomes a group. And the key equation, let's call this background field 2, and again this one A3. The key equation is again that G4, the gauge invariant field strength, is dA plus there's now a little bit of an interesting factor that's to work out by studying instantons. So this is the key equation. So you again find a higher group in this non-abelian SUN coupled to an axion. Now there are also examples involving, we can also add massive flavors. I don't want to bore you with that kind of Baroque example. Instead, I want to do something with this. So far, it's been a little bit of a technical show in terms of we have all these symmetries of different degrees, form fields, background fields, Green-Schwarz mechanisms, etc. You could ask, could you derive any new physical facts from this this symmetry? And I'd like to derive one.
Yes, and the modifications of your background field couplings would first show, if you computed correlation functions for currents or for charges, would first show up at 3-point function levels.
Yeah. Mm-hmm.
Okay.
Yeah. So usually when you look at the it's extremely similar, Shiraz, to how you discover the structure constants of a non-abelian global symmetry and in current correlation functions, right? So then you would find that J collides with another J and produces a third J with a FABC.
Right.
Here you find something similar, except for you often find like derivatives on the J's, so that to accommodate the fact that the currents have different space-time dimensions.
Right. Right. And it would change. It would. Right. Fine. Thank you.
Yeah. Okay. So good. Okay. So let's do something with this. So, oops, what happened here? Okay, let's just discuss one application.
So the
constraints,
operator product expansion that you just talked about, that there the J's are to be thought of as local operators, right? For any form degree.
Mm-hmm.
Okay.
Yeah. So so the case that I've discussed up here is a little more complicated than that because I have discrete symmetries. So the discrete symmetries won't have a friend J coming along with them.
Right.
They'll just have these charge operators, which are these surfaces or domain wall operators. And then you'll have to look at the operator product involving those. But you can still see it in terms of 3-point functions involving those.
I see. But for local currents, you will not see any non-trivial 3-point function as a result of
in this case, you won't just because the discrete symmetries don't have associated currents.
Yeah. Okay. No, I mean there could have been
there are other
where no, I mean in this case also there could have been a structure where 3-point functions involving continuous symmetries appear. The two continuous symmetries appear. They just
yes, but the way no, but the way if you look at these formulas, Abhijit, look at these formulas, the way it comes out in the end is that the nonlinear term in G4, for instance, involves only the ZK electric one-form symmetry.
Yeah.
So it doesn't involve the continuous magnetic symmetry. Yeah.
Right. In this case, it does not. Yes,
it's not a universal. It's definitely not. Oh, sorry. Go ahead.
Oh, so I guess more general question is algebraically, are these structures constrained similar to the Jacobi identity for FABC?
Yes, but it's well,
Can
I
one
can
aim to
try and explain. I mean,
them
I don't
like
know how to
that?
say the answers. I don't know how to say what the constraint is so succinctly as the Jacobi identity, but I know that there are some kinds of constraints from like associativity of fusions and things like that.
Mhm. Okay.
Okay, so okay, let's go through this application. So we're going to be focused on axion Yang-Mills. And what I first like you to notice is that this is not UV complete. Right, the interaction term is a dimension 5 operator. So if one writes down the theory of axion Yang-Mills, you must be thinking of it as some kind of effective field theory. And so we should think of it in the context of a renormalization group flow. So let's here have axion Yang-Mills. Here will be some UV theory. And we'll be considering an RG flow, which realizes this axion Yang-Mills at long distances as the effective field theory. Now, there are several energy scales that one can associate with such a flow. So the first I'll call E string. This is the scale at which U12 becomes a good symmetry. So we have a flow. We know we get to axion Yang-Mills at long distances. We know that the two-form string symmetry is a symmetry of axion Yang-Mills. So we can say there's some energy scale at which that symmetry becomes approximately valid. Now we can say a similar thing for another scale. I'll call it E screen. This is the scale at which the Zn one form symmetry emerges. And given these two scales, we have a little result. E string is always greater than or equal to E screen. Okay, so first of all, whenever you see this symbol in physics, you get nervous. Why this? Why not strict less than or equal to or something mathematically more precise? Well, these scales are only approximate. So the energy scales that I defined above, I only defined them approximately. So I can't give you a sharp inequality. But what I mean by this result then is that the converse is impossible. So you can never have, this is impossible. And this is a sharp statement. So you can't parametrically separate E screen to be larger than E string in any renormalization group flow that terminates in axion Yang-Mills. Okay. What's the proof of this result? Well, it's essentially trivial given what we wrote. So let's remember I wrote for you that G4 is dA3 plus Kn n minus 1 B2 B2. All right, this is This was our key equation that was telling us that we had this interesting higher group symmetry. So what do you do with it? Well, so if Zn1 is a good symmetry, this implies we can couple to B2, which implies we have G4 flux. This is the step where I'm using this equation. And of course, this means that we have U12 as a symmetry. So once you have the Zn1 form symmetry, you already have the 2 form symmetry. And that's what this inequality that I wrote here actually says. So that's a kind of slick proof. It's not clear if it has teeth. It's not clear what it really means maybe to you. So to conclude the talk, I'll spend a few minutes going through a concrete example of how it works in practice. But before doing that, I want to pause to see if there are any. Okay, so let's do an example. Pecha-Quinn axiom. Okay, what's the Pecha-Quinn axiom? Statement about it's a RG flow that gives us axion-Yang-Mills at long distances. Go through it lightning fast.
Sorry.
Yes.
Just to make sure I understood your proof. If I understand, right, you say that there is something on the right-hand side of this equation, so the left-hand side cannot be. I mean, that's pretty something that saturates it on the left-hand side. Is that correct?
Exactly. Yeah.
Okay, but
that's correct. It's a completely trivial argument. It just, if you like, in terms of the OPE, it's even more transparent. It's just saying that, like, once you have this Zn1 form symmetry, you have some surface charge operators, and their operator product expansion includes the current for the 2 form symmetry.
Yeah.
So it's just not logical to say that you have one without the other.
I see. And
it's a kind of algebraic statement.
Right. Okay. Thank you.
Yeah, it's very similar to saying, imagine I have, in SU2, I have the J plus and J minus currents. Then you learn that you have J3 from that. This is the same. Okay, so let's do this.
Right.
Go ahead. Yes.
Could you imagine a theory with, well, I'm just trying to understand the logic of that. Suppose I had, I just didn't have this G4 symmetry. You say that this equation gives you an operator, this G4, and from the fact that this G4 exists, you know that there is another conserved current, something like that, right?
Yes, because G4, I mean, it couples, or A3 that couples to the current in a linear fashion in the action. So varying the, considering the theory in the presence of A3 is like considering a generating function for that other current.
And that it's a current that is necessarily conserved is somehow built into the fact that this was a G4.
That's a gauge field. Yeah.
Okay.
Sorry, that A3 is a gauge field and G4 is a field.
I thought the assumption is that at low energies you do get axion-Yang-Mills theory. So you know what currents you are going to end up with at low energies. And only in that scenario can you say this, right?
Yes.
I see.
Well, what I can say is that any theory that has 2 group or higher group global symmetry with this kind of structure constant, the K is playing the role of structure constant, which has a non-zero structure constant there, must have the feature, it essentially has the feature that the Zn1 one form symmetry is not really a subgroup of the global symmetry.
Right. No, but
So
just from the existence of G4, one cannot conclude that it must have the additional term on the right hand side, right? You need to know that the
No,
theory
you cannot.
in the IR needs this structure. Has this structure.
Yes. I'm putting that in. I'm putting that in. I'm putting in that I know that I'm going to hit a non-zero value of K.
Yeah. Okay.
Yeah, exactly. I'm putting that into the argument. Right. There are plenty of theories that just have a U1-2 form symmetry. There are plenty of theories that just have a Zn1-1 form symmetry. The additional thing that I'm putting in is I'm saying I know that in axion-Yang-Mills, those things are fused into this higher group structure. And then I can get some energetic inequality.
Yes.
Thank you.
Okay. So let's look quickly at this Peche-Quinn example. So let me just write the action. So, okay, so we have SUN gauge fields. We have psi plus minus, which are Weyl fermions in the fundamental and anti-fundamental respectively. We have a complex neutral scalar. We call it phi. Neutral meaning uncharged under SUN. Then there's some couplings. So there's Yukawa terms. And then there's a potential. Or phi. Let's call this quantity B of phi. Okay, so that's the UV Lagrangian. No axion in sight yet. Let's do the standard analysis. Is it okay if I go a few minutes more, guys?
Yes, Clay, go ahead.
Yeah, okay. All right. Okay, so the standard analysis is quite straightforward. So first of all, it's clear that the potential makes phi want to sit at absolute value F. So then you phi in radial coordinates, you write it as F. Well, not yet F. Let's call it rho, a radial mode, e to the I A over F. And the mass of this rho radial mode is like m times F, where m is the constant here that I wrote in the potential. So rho is massive and gets frozen out. So below that scale, we can look at the Yukawa term. This gives us lambda F e to the minus I A over F psi plus psi minus plus complex conjugate. Now, the trick is that you do a chiral rotation on the fermions, and by that you can remove the e to the A over F term, this exponential interaction. So you can just get this to be this form. But you pay a price because this chiral rotation is anomalous. And the price you pay is some number that you get to work out times A F wedge F, the axion term. Okay, now it's easy. The fermions are massive. So the masses of the psi fields are lambda F. And then we integrate out. To axion-Yang-Mills. Okay, so that's the standard analysis that shows that the kind of action that I wrote for you above leads to an axion-Yang-Mills theory. And so this is the kind of theory that our inequality on energy scale should apply to. So let's see what it really means and how it works. Okay, so what are the scales? Okay, so first one is easy. What is E screen? Remember, this was the scale where the one form symmetry was broken. That means it's a scale where charged matter appears. So this is like m psi, which we learned is lambda f. This is where Wilson lines can be screened. Okay, what about E string? That takes a little more thought. So let me write the answer and then I'll try to justify it for you. So I claim that this is like the fourth root of the potential, which is like root mf, the fourth root of the potential evaluated at the origin. So what was E string? So E string was the energy cost, the energy such that above that energy, there's no more of these conserved axion string charges. So that is the scale at which you can tell that there's not really a periodic scalar in this problem. At low energies, there's the periodic scalar A, but at high energies, there's not. At high energies, there's just phi. So the question is, what is the energy you need to probe the fact that that rho can go all the way to 0? And that's why you get this this energy scale here for the string scale. Okay, so the inequality string greater than or equal to E screen now says a little bit interesting. Now it says that lambda, the Yukawa coupling, is less than or equal to square root of m, this potential scale. This is an inequality among dimensionless coupling constants in a Lagrangian. So you could ask, why is this true? Is it true? So I claim that this is true, though not in a completely obvious way, that this Yukawa coupling is less than this, this potential term. And to see it, we should, what we should do is we should examine the Coleman-Weinberg potential. So you see, when I went through this analysis, kind of la-di-dying my way into axion-Yang-Mills, I just said, well, we just look at tree level, everything is fine. But what we'll see is that this story that we discussed here can be modified in some way if we take into account one loop correction potential from integrating out the fermions. So let's do that. So the true effective potential, it depends only on the absolute phi. And it looks as follows. So, so first of all, there's, of course, the tree level term that we wrote, m squared mod phi squared f squared squared. This was the tree. But now there's an important one loop correction. I'll even write for you some pi's. So this is the Coleman-Weinberg part. And big lambda UV is the cutoff. Okay, so now you could ask, where is the true minimum for the scalar field phi? So let's look in large cutoff. The true minimum for phi.
So, and this potential was obtained by integrating out the fermions.
Exactly, yes. Just the fermions are quadratic, easy enough to integrate them out. Yeah. So I'm doing the standard thing. I'm just adding up the 0-point energies for the modes as a function of the VEV of phi. And what you find is that, well, the expectation value, the true place where phi wants to sit can be written like this.
This,
Yes.
what is the capital M?
Capital M.
N.
Where's capital M? N of
capital
SUN.
N. Ah, okay.
N SUN. The number of colors.
So there is some gauge. There is some the effective potential is also due to
there's a loop of there's a loop of fermions, and the number of them, since they're in fundamentals, is proportional to n.
Oh, okay, that's the fundamental. Okay, fine. Yeah. Thank you.
Yeah, that's all that's happening.
Yeah.
Okay, so let me look at large cutoff in the region of interest. And here I'm ignoring some finite shifts that are not important for what I'm talking about. So let's look at this inequality star. Let's call it star. So what happens if star is violated? Then that means that lambda squared, the Yukawa coupling, is much bigger than the quartic coupling M. And then you would find that this would be larger than the UV cutoff. That's bad news. So this means that the effective field theory breaks down. Right? Whenever you try to take a scalar with a VEV that's larger than your UV cutoff, you're probing strong coupling. More technically, you could think that I'm losing control in this example because I've neglected in the potential terms like phi to the 1,000 over lambda to the 1,000, but those would be becoming important in this limit. So you see that this what I'm telling you is that the inequality that we found for symmetry purposes is actually enforced just by the self-consistency of the effective field theory. It's secretly buried in there, even if you didn't know it, that there's this constraint on the strength of the Yukawa coupling relative to the quartic. And this can all happen at weak coupling. So the couplings here can all be much smaller than 1. And this inequality is still interesting. So this is an example of the kind of physics you can get out of these higher symmetries. You can learn about some constraints on dimensionless coupling constants in Lagrangians. Okay, so please ask me questions. There's more examples in the paper. Yeah, thanks very much.
Thank you very much, Clay. Thanks a lot. Are there questions for Clay?
So just going back to a question Abhijit asked sometime during the talk, when you have these structures that mix symmetries of various ranks, is there a mathematical framework within which such symmetries fit?
Yes, there is, but it's a little bit of a mouthful. I think it's probably much easier if all the symmetries are continuous. If you ask me to define, what the answer is, for the discrete case as well, I can do it, but I don't know if you'll like it. I mean,
fine. So let's stick to the continuous case first.
Yeah. So the continuous case, I mean, I think the kind of thing that you would want to study is the continuous case. I haven't worked it out in complete detail, but I think it just boils down to studying fusions of currents involving where the right-hand side of J1 collides with J2, and the right-hand side is some derivatives of J3, basically, with some epsilon symbols. It's pretty.
I was wondering the following. In the case that you have a normal group, it was very profitable to study representation theory of that group.
Yes, that's an excellent question. So you can ask, what's in a representation of this funny symmetry? Yeah. So so that's something that I'm kind of thinking about, but the answer seems to be, so you need a kind of operator in quantum field theory, which talks to form symmetries of different degrees. So, you know, a point operator talks to an ordinary global symmetry, a line operator talks to a one form symmetry, etc. So you could ask, imagine you had some kind of one of these algebras where a one form symmetry is mixed with an ordinary symmetry. And then I think the kind of thing that you want to study are like point operators that live at the end of lines, basically. So like ray operators.
Okay.
So you know it's something like that, like junctions of operators of different dimensions, basically, that can be charged under both.
And these, suppose I just took this theory, put it on an S3 and quantized it. Should I expect a representation of this structure on the space, the Hilbert space of that?
So you would probably need to look at you will need to look at a space manifold which is richer. If you just try to look at S3, you won't have enough topology to activate the. I mean, that's true even for like before we look at these fancy mixtures, we could just say like, you know, suppose I look at Maxwell theory. I told you up here that Maxwell theory had two one form symmetries, right? It has the U1 electric and U1 magnetic. Where did I here? Right. So you could say, well, okay, how is that manifest in the Hilbert space of the theory? If I quantize it on S3, I won't see any representations of that. Right. There's no, you know, the local operators are not in representations of these groups.
Right.
But if you quantize it, say on S2 times S1, you will see it. So
Right.
in order to sort of start activating, finding representations of P-form symmetries, you need to be on space manifolds that have P cycles.
Okay. Okay, great. Thank you.
So are there any study of these higher group symmetries in the math literature? I'm thinking about like defect operators and, you know.
Yeah, so in the math literature, I mean, the math literature is actually where the name higher group came from. Yes, there is a study of them. There is a kind of complete theory of what classifies them. It's just a little bit of a mouthful, which is why I didn't use it. But there is a complete theory of supposedly of higher group symmetries. Though I have, to be honest, I have not penetrated super deep into that literature. It gets a little heady.
Mm-hmm. Okay.
But yes, if you Google higher groups,
Mm-hmm.
you'll get to math articles very quickly.
Okay, thank you.
So Clay,
Mm-hmm.
one question. So just like the standard operator product expansion for local operators, in conformal field theory, one sometimes also talks about operator product algebra associated to a local operator when you take it close to a defect.
Yeah.
Such algebras, would they probe this structure?
I think so. Yeah, it sounds to me like they would.
So have you thought about looking at this from an abstract point of view? Just you know, kind of a CFT spirit, operator algebra spirit.
Some, yeah. So I mean, you know, so I wrote a previous paper on a restricted class of higher groups that just involve zero form and one form symmetry. And those are very common, especially like in Chern-Simons matter theories in 3 dimensions and TQFTs. So in that case, we were able to indeed write down a kind of operator fusion algebra just among, we didn't think about it in terms of a local operator approaching the defect. We just wrote it in terms of the charge operators. So in terms of the domain walls and the surfaces and things like that. But that's kind of similar to what you're asking. You can then express those things if they can be in terms of integrals of currents and try and work out what it means there. But yeah, so we tried to do that sense.
Also, you
But
mentioned that.
go for it. Sorry.
No, I was going to a different question, but please do finish.
Oh, all I was going to say is that I don't feel that I have a good enough grip on the set of possibilities that are relevant for physics yet. If you broaden outside of that more restrictive class. So this paper is an example that exists outside of that class. So the question is sort of, there's this kind of fancy topic of higher form symmetries. You can ask which higher form symmetries are really relevant to physics. So obviously we often have ordinary global symmetries. We don't even need to discuss that. But since we like gauge theories so much in physics, we often have one form symmetries, either continuous or discrete. And what I didn't really appreciate until this paper is that there can be interesting situations where we also have two form symmetries, namely these axion kind of examples. But if you're in low enough space-time dimensions, that might be it, just 0, 1, and 2 form symmetries. And so then you're kind of in a more restricted situation than this general mathematical setup where you could have form symmetries of all possible degrees mixing in all possible ways. And it might be a worthwhile thing to classify just this more restrictive thing.
Right. Okay. So I remember in your, a paper that you wrote, I think a few years back, perhaps with Thomas and Ken also, about this two group symmetries. There also, did you have an associated energetic inequality, energy scale inequality?
There is an associated energy inequality. Yes. Yeah.
And there also you could see this realized in certain concrete examples.
Yes, but the examples were sort of not as rich as these examples. Maybe someone knew it, but I didn't know a priori that there existed this inequality on dimensionless couplings in Pechequin type models. The inequalities that we seem to get in the other cases looked more obvious.
I see. Okay, thank you. Any more questions? Must be midnight there, right? Already?
That's okay. Yeah, almost.